In today's session, I'm going to talk about principal component analysis (PCA). So PCA is a pre-processing technique and not a machine learning algorithm. It is used to do pre-processing, that is to reduce dimensions. So dimension reduction means number of features reduction. So what happens is that when you have a number of features in your data set, like thousands of features, so you need to reduce the dimensions like that. For that, we use dimensional reduction component, which is principal component analysis. So let's say in dimensions we have 1,000 features, and we need to reduce to five or seven or eight features. Okay. So let's take an example. So let's take an example where personals are standing over here for a photograph. So if you click photo from here, so this person will be visible, this person will be visible, this person will be visible, this will be, he will be visible, he will be visible. This person will not be visible because he is standing backside to him. Okay. So what happens is that so we will be able to cover one, two, three, four, five, six personals from here. If we take click from here, this person visible and this person is visible because this person is standing behind this and this person won't be visible. So, so this is known as variability. So variability is the spread of data points. Okay, this is the spread of data points. So principal component can be able to tell how much variability it is capturing. Okay, so let's say we are taking principal component from this here. Okay, so we are able to capture six personals. Okay, from here. So let's say the next we will take capture it from here. So we'll capture two persons. So next we'll capture it from here. Next we will be capturing these two persons. So this guy will be coming. So okay. So this is how it happens. So this is the variability. So variability is the spread of the data points. Principal component can be able to tell how much variability it is capturing. Okay. So PC1, so let's say, so when you have a variability like 1,000, so variability 1 till variability 1,000, so then we will have principal component 1 till principal component 1,000. And that 100% variability will be covered using all the principal components, okay? So using all the principal components, you'll be able to cover 100% of the variability. So PC can be able to tell how much variability it is capturing. Okay, as this variable one PC component will be able to capture almost maximum variability, that is variability one. So then the PC one captures highest variability. Then PC2, principal component two, will be, capture less variability than PC1, and then PC3 will capture less variability than PC2. So it moves on, okay? So, but at the end, if you take all the principal component, it covers all the 100% variability. So this is an example, like PC1 will be able to cover 50% as is shown here. So if you take image from, if you take a photograph from here, so it will able to cover most of the person. And PC2 covers less than PC1 and will be always be more than PC3. So PC2 covers 20%, let's say PC3 covers 10%, and PC4 covers 4% of the variability. Okay. So if you consider first five principal component, then you could see that 86%, 50, 20, 70, 70, 80, 84, 86% of the variability is covered. Okay. So so this is how we will be able to capture data points or the feature variability using principal component analysis. Okay, you need to understand how much of the principal component we need to consider. So based on the kind of output you are dealing. Okay. So now let's talk about covariance matrix. Let's say we have X and Y, the variables. So we will give covariance of X to X, then X to Y, then Y to X, then Y to Y. We'll calculate covariance of these and we'll put it in the form of matrices. Okay. So the next is the steps involved. Okay, steps involved is first you need to import data, then you standardize and find covariance matrix, that is covariance COV. Okay. Then you need to find eigenvalue, which is the scaling factor, and then you have to find the eigenvector as well, which is only scaled but not rotated. Okay. Then you need to define a principal component, which is the dot product of eigenvector and standardized column. So, and also, if so, the reference is A dot B, vector A dot vector B is AB cos theta, where theta is 0 at 0 degree is 1 AB, and theta at 90 degree A dot B is 0. So if scaling factor is high, then higher the variability. You need to understand scaling factor, if it is high, then higher the variability. Highest scaling factor in that direction is PC1. Second is PC2. Okay. So now let's look at more theoretical part in principal component analysis. So the dimensions of a data set is defined as the number of input variables or features. Okay. So dimension is nothing but the number of input variables or the features that are present in your data set. Dimensionality reduction is the process of reducing the number of variables in a data set. Let's say you have a very large number of features in your data set, then you need to reduce the number of variables in your data set. So we perform dimensionality reduction in that case. The curse of dimensionality exacerbates difficulty of modeling predictive modeling tasks. High-dimensional statistics and dimensionality reduction are commonly used in data visualization. These methodologies can be used in applied machine learning to simplify categorization or regression datasets in order to improve predictive model. Okay? So these methodologies like principal component analysis is used to reduce the dimension for classification or a regression problem in order to improve predictive model of prediction of model. Okay. This article will discuss dimensional reduction in the context of machine learning. Okay. So algorithms for machine learning frequently struggle with big features sets as inputs. So when you have a lot of very huge number of features or variables, then your algorithm prediction will be difficult, or the model will find it difficult to do the prediction. So dimensionality reduction is the process of reducing the number of features in an input. So this is what I will discuss. So in the input are the predictors, we are trying to reduce the number of predictors so that it is easy to capture all the data points or the output using the less number of features that we are considering. So dimensionality reduction techniques include feature selection. So this is all about like feature selection. Okay. So we will select some of the features from a lot number of features. So like feature selection is a subset of the population features. Okay. And also numerous input variables problem. So an excessive number of input variables can impair machine learning performance. So we already know that. So the more the number of features or the input variables, the more the problem of the performance of the machine learning. The input variables in the spreadsheet refer to the rows that are entered into a model to forecast the target variable. Yes, features are considered to input the input variable. Yes. Also, features we already know that we are considering features as their input variables, and these features are used to do the prediction or forecasting of the target variable. So columns represent dimensions and rows represent points in an n-dimensional feature space. So we have already known this as well. So columns represent dimensions. So we are going to reduce the dimension, and rows represent the points in an n-dimensional space. This is somewhat accurate geometrical representation. For example, the presence of multiple dimensions in a feature space results in a vast volume, and hence the points reflect a small and non. When working with huge data set, the curse of dimensionality can significantly hinder the performance of machine learning. Yes. When you're working with huge data set, the more the dimensionality of input variables, then the performance of the machine learning system can be hindered. Okay. So thus it is often described to reduce the total amount of input features. So this is actually done when you're doing the prediction. So you have to reduce the number of input features. So that is the desirable one. This results in the reduction of dimension of a feature space. Okay. So now let's come to dimensional reduction. So dimensional reduction is reduce the number of variables in training data using the following techniques. It is advantageous to reduce the number of high dimensional data by projecting it into a lower level space that encapsulates. It is known as reduced dimensionality. Hundreds of thousands, if not millions, of input variables are possible. So reduce input dimension frequently equate to fewer parameters or a more specified, simplified machine learning model structure, referred to as degrees of freedom. So a model with an excessive number of degrees of freedom may overfit the training data, results in poor performance on the data. Okay, so you don't have to worry about these many things. So just understand that we have to reduce dimensions in your model if there are a lot number of features you are dealing with. This is because there are some of the problems that might occur while doing the prediction of your model because of large number of dimensions. So only use principal component analysis when you have huge dimension and you want to only you want to select a specific number of feature selection you need to be doing. So your model will be able to cover like 90 or 90 more than 90% of the data features. Like 90% of the explanation can be given by the features that you have selected. Okay. So we have already seen how principal component works. So higher like so we will be able to do the plotting and check how many principal components we want. In the next session, I'm going to do a coding for a pre-processing technique like principal component analysis, where I will be showing you how many principal component analysis you will be requiring for a particular data set by doing the plotting. And this is all about principal component analysis theoretical part. Hope you enjoyed the session. I will be seeing you in the next session for further discussion regarding principal component analysis. Thank you so much for attending the session.